Okay, welcome back everyone. We are here to talk about inverse trig functions, and by now we're very familiar with trig functions. We know all about sine, cosine, tangent, and the others, and we want to see what we can do about creating some kind of inverses for these functions. So let's go ahead and get started. So we're going to go through the trig functions one at a time and sort of talk about the inverse versions of them. So we'll start with sine and cosine. And what we want to get to is some form of inverse sine. And we need to talk about, is there even such a thing as inverse sine? The main idea is, what if we know sine x and we want to know x? All right, so we know the sine value, we know the function value, sine of something, and we want to know what was the input, what x value was being input into sine to get that number. So we need an inverse function because that's what inverse functions do. We need an inverse function. All right, but there is a problem here. I wonder if anyone can think of what the problem is. Sine is not one-to-one. You know that we say that inverse functions exist for any one-to-one functions? Here, let's draw a little picture. Let's draw a quick picture of sine. So let's say here's pi, here's 2 pi, negative pi, negative 2 pi. All right, so we know what sine looks like. And what I'm drawing here, just to be clear, this is going to be a picture of sine. I know I put the heading inverse sine, but I'm drawing a picture of sine right now. It goes up, comes down, down, back up. So I can tell from the picture that this is not a one-to-one function, right? Because, here, let me just indicate that this is f of x equals sine x. It fails the horizontal line test. Let's put that in parentheses. So that's how I know that it's not a one-to-one function. And that means that if we're going to somehow have an inverse, it's not really going to work, or it's not going to work for the entire function. It can't. You can have a horizontal line that touches more than one point on this curve. So we are going to do a little trick here. We're going to say that the function f of x equals sine x is one-to-one if we restrict the domain to the interval negative pi over 2 to positive pi over 2, square brackets. This is a trick that's going to let us create an inverse version of sine. The new picture of it would be what I'm going to draw here is another picture of sine, but this time I'm only going to allow the domain to be this interval. Typically, the domain of sine is all real numbers, right? It keeps going as far to the left as you want, as far to the right as you want. Here's pi, 2 pi. What happens if we say, let's just draw part of the picture. We're going to draw the part from negative pi over 2 to positive pi over 2. So that is going to look something like this. It's less than one period of the function. So this is f of x equals sine x with its domain restricted. To only be part of the usual domain. And you might say, are we allowed to even do that? Are we allowed to just take a function and make, say, okay, we're going to make the domain smaller? I thought that the domain of sine x was all real numbers. And the answer is, we're allowed to do this. We're allowed to make this switch as long as we understand that what we've done is we've kind of created like an alternate version of sine x. It's not truly sine x anymore. It's now like a different function technically because it has a different domain, but it acts exactly like sine x just on this region. It's almost like we took the graph of sine x and zoomed in on just this region that we're interested in. So we're allowed to do that. Okay. Then an inverse exists. Because this passes the horizontal line test, right? That's what we've been trying to do. Passes horizontal line test. So it is 1-to-1, so it does have an inverse function. So we're going to make an inverse of this. This smaller version of sine is going to have an inverse. So we have a definition. And it says the inverse sine function denoted sine little -1 up there. We're going to talk about that notation in a minute, but that's how it's written. Is the function with domain -1-1 and range -π/2 to π/2 defined by inverse sine of x equals y whenever sine of y equals x. I'll give you a chance to see that. Underneath, I'm going to write inverse sine of x is the number in the interval -π/2 to π/2 whose sine is x. That's what we're getting at. I'll show you some little examples of this being used. We're saying inverse sine of x equals y whenever sine of y equals x. This might look a little weird to you because sine of y, that's usually not something that we say. We usually just talk about sine of x, right? But we are purposely switching x and y here because when you talk about inverse functions, the x's and y's kind of get swapped. But the main thing to take away from this is that inverse sine of x is the number in this interval whose sine is x. So let's do some concrete examples here with actual numbers in them. Let's evaluate. I'll do these first ones for us. I think I'll have some later that I'll ask you to do. Inverse sine. And that's how we pronounce this. We pronounce it inverse sine. And I'll write a few parts. I'm going to have part A, part B, part C. We'll talk about, like, some of these might not be defined. Some of them might just be does not exist, but let's see what happens. Okay, so I wrote 4 of them, and I'm going to go through these. Let me just move the page a little bit. Okay, that last one has inverse sine of 1.25. All right, so for part A, inverse sine of the square root of 2 over 2. The square root of 2 over 2 is definitely a familiar number to us. We've been using that a lot these past couple of weeks. That number's shown up. And we're basically asking, if I say, what does this equal? I'm saying, I'll remind you, what number in this interval has a sign equal to the square root of 2 over 2? Is there a number in this interval that when I take the sign of it, I get square root of 2 over 2? And yes, there is. Pi over 4. Right? Because sine of pi over 4 is the square root of 2 over 2. Pi over 4 is the number in that specified interval whose sign is square root of 2 over 2. By the way, you might say, wait a second, isn't there other numbers that you could put in also, like not just pi over 4, but aren't there other things that also would get you the root 2 over 2? So let me talk about that real quick. So note, like what if we drew a unit circle? We do scratch work unit circle, and we say, I want to know when is the sine of something equal to the square root of 2 over 2. And you might say that it happens here. And you might say that it also happens here. You know, you could go this far around, but it also feels like, couldn't we do this? Sine of both of these is the square root of 2 over 2. What I'm saying is, note, sine of 3 pi over 4, that's what this longer one is, equals the square root of 2 over 2 also. But what's the problem with this one? Why did I say the answer was pi over 4 and I put a box around it? And I'm saying definitively that is the only answer. Why not this one? Why not 3 pi over 4? It's because 3 pi over 4 is not in the specified interval. So it is not an answer to this question. So that was a little side note to talk about why this other thing almost looks like it would be an answer, but it's not, because it's not in the correct interval. So there's only one answer to each of these questions when we talk about inverse sine. And there has to be only one answer, if you think about it, because the title of this section was inverse trigonometric functions. So if this thing is called the inverse sine function, if it's a function, then each input can only have one output. That's part of what it means to be a function. Each input can only have one answer, okay? So I'm telling you this just because sometimes in the past, in previous semesters, I've seen students list like 2 different answers, and that's wrong, because there can only be one answer to each of these problems. The answer might be does not exist, but you'll never have like 2 different numbers. All right, I said a lot about part A. Let's do the other parts a little bit quicker. So inverse sine of 1/2, we could do a scratch work unit circle for each of these if we want. You basically want to find a number in that interval that when you take sine of it, you get 1/2. And I think about the familiar sort of values that show up. Do any of them give me 1/2? And yes, pi over 6. Pi over 6 is the answer. And that you know, if you wanted to write this, you could say it's because sine of pi over 6 is 1/2, and because pi over 6 is in the designated interval. Inverse sine of -1. So is there a number in that interval that when I take the sine of it, I get -1? Yes. It happens to be negative pi over 2. That's one of the endpoints of the interval. But, you know, the interval has square brackets, so the endpoints are included. So this is allowed. You can check that sine of negative pi over 2 does equal -1. So that checks out. Inverse sine of 1.25. So is there a number in this interval that when I take the sine of it, I get 1.25? Well, doesn't seem like it's any of the common values that we've worked with. Pi over 4, pi over 2, pi over 3. Doesn't seem like it's any of those. This is undefined. Undefined or does not exist. How do I know? How do I know that? Not just because we don't say it's undefined just because it's not one of the common numbers we know. The real reason why it's undefined is because 1.25 is not in the domain, which in the definition, the domain was said to be -1 to 1. This is too big. Now, do we need to memorize that this is the domain? If you think about it and you really understand what inverse sine means, you should know that we can't make sine of something equal 1.25. There's nothing I could put in for that question mark that would make this work. I'll tell you 2 ways that you could visualize that. One is on the unit circle. You say, where on the unit circle would I ever reach a height of 1.25? You're never going to be on the unit circle if you're that high up. 1.25 is up here above the unit circle. So that's one thing that tells me that this doesn't exist. Another thing is if you take a quick look at the graph of sine x and you say, the highest that this graph ever goes is a height of 1. The lowest it ever goes is -1. So if you ask me sine of something equals 1.25, we're not even on the graph anymore. So that can't happen. So if you ever see something like 1.25 or anything bigger than 1 or smaller than -1, undefined. So I think that that's probably enough about inverse sine. Let's talk about inverse cosine. And now that we spent all this time on this one, we could do inverse cosine a little bit quicker. So let's move the page up and talk about inverse cosine. We're going to kind of develop this in the same type of way. I'm going to start by drawing a quick sketch of the graph of cosine. I know the max height is 1 and the minimum height is -1. We could go out to at least pi and -pi. All right. Let's mark pi over 2 and -pi over 2. So this graph looks something like this. All right, looks something like that. And again, the graph of cosine ordinarily would fail the horizontal line test. It would not be 1 to 1. and there would not be an inverse version of cosine. But we can make it a one-to-one function if we restrict the domain, if we sort of just chop up the graph and look at a part of the graph and focus in on that modified version of cosine that has a smaller domain. So we're going to say cosine is one-to-one if we restrict the domain to... Let's think about this. Can we use the same interval that we did earlier? I still have it up here at the very top of the screen. Can we use that interval, negative pi over 2 to pi over 2? That's not going to work. It's not going to work this time. If we use that interval, we're just going to have this kind of bump that fails the horizontal line test anyway. So we can't use that. We can't use that hill. It fails the horizontal line test. There are some other regions that we could focus on instead. What if we start at 0? How far can we go before we would have an issue with the horizontal line test? We could go all the way to pi. And that's what we do. 0 to pi. So I think what I'm going to do, instead of drawing a second picture, is maybe I can just kind of shade in, you know, if everyone's all right with that, I'm just going to shade in the part of the graph that we're focusing in on. But draw a second picture if you want, like we did for inverse sine. So I'm saying if we focused in on just this part of cosine, that's from 0 to pi, right? 0 to pi. We get a portion of cosine that is one-to-one, and we can make an inverse function based on this. So I'm going to go straight to the definition. And after the definition, we'll do an example problem. The inverse cosine function, denoted cosine with a little -1, is the function with domain. Domain is same as before. It's still -1 to 1. And range 0 to pi, defined by, we define it so that inverse cosine of x equals y whenever cosine of y equals x. Underneath, I'm going to write a sentence. Inverse cosine of x is the number in the interval 0 to pi whose cosine is x. All right, let me section that off a little bit just so it's easier to see. There's the definition, and then there's my little remark at the bottom. I'll give you a chance just to see all of that, and then we're going to do an example problem. So I'm going to ask you to try this one. I'm going to give you just 2 parts. I'm going to say evaluate, kind of like I did before on the inverse sine problems. In fact, I'm going to give you part A is going to be an inverse sine problem, and part B is going to be an inverse cosine problem. And I'd like you to take a minute and think about this, maybe pause the video if you need to, and then I'll talk about it in a minute. All right, now remember, it is possible sometimes these problems just have an answer that does not exist or undefined. So let's keep that in mind as a possibility. I'm going to do a scratchwork unit circle and say part A. Draw the unit circle. And I'm thinking that I want sine of something. Here, let's write it. We want sine of something to equal negative square root of 3 over 2 for part A. So I basically want the y-coordinate on the unit circle, sine, the y-coordinate to be negative square root of 3 over 2. And I can think of a place here where that happens. I can think of a place here where that happens. It kind of looks like maybe there's two answers, but only one of them is going to be in the correct interval. And that is if I use this one. I'm going to say that inverse sine of negative root 3 over 2 is equal to negative pi over 3. And notice that this is in the specified interval for inverse sine. What do you think? Does that make sense? I realize this is a pre-recorded video, so sometimes I just ask rhetorical questions. This makes sense because we're looking for a place on the unit circle that when I take sine of it, I get square root of 3, negative square root of 3 over 2, and I think about common values that we know, and I think about where on the unit circle we need to be. And instead of going, like, what if we went the positive direction? Like, what if we looped around counterclockwise until we got to this same terminal point? The problem with that is we would get a large number that's technically not in this interval, and it would be wrong. It would be coterminal with this, but it would technically be wrong. There's only one correct answer, and it's negative pi over 3 because that's in the correct interval. So if you went like all the way around and you gave like a positive answer, that was like a bigger thing, you know, that might be like a partial credit situation, but it's not technically correct. So the next one, I'm asking about cosine of the same number. Is it the same terminal point? Well, no, it's not the same terminal point. It's not the same part of the unit circle, because this time we want the x-coordinate on the unit circle. Want the x-coordinate to be negative square root of 3 over 2, right? So that's different from having the y-coordinate. So I think we want to go here. Somewhere about here. Remember on the unit circle, like here's 0 and here's pi. There's another place on the unit circle that looks like it's got potential, that maybe it has that same x-coordinate. But I need to be between 0 and pi. So I guess you could say that with inverse sine, when we restrict the domain, maybe this will help. I'm going to get out a highlighter. With inverse sine problems, we need to be in this half of the unit circle. I don't know how well the highlighter shows up on the screen, but let's say, yeah, it's not bad. For inverse sine, you need to be there because you want to be between negative pi over 2 and positive pi over 2. For inverse cosine, you want to be between 0 and pi, so you need to be in this half of the unit circle. So it's not the same for inverse sine and inverse cosine. They each have an interval that they need to be in. It's the same size interval. It's just right half of the unit circle, top half of the unit circle. So this point here is going to be the correct one. So inverse cosine of negative square root of 3 over 2 is, where is this? This is 5 pi over 6. That's a positive 5 pi over 6. And you can notice that this is in the interval from 0 to pi. It's almost as big as pi. Okay, so we've talked about inverse sine and inverse cosine, and we've done a couple of problems of evaluating them. Let's talk about the next one, inverse tangent. It seems like for each of these, I've started by drawing a picture of the graph. I drew a picture of the graph of sine. I drew a picture of the graph of cosine. Let's draw a quick picture of tangent. Remember what that looks like? Let's say this is pi over 2. Let's say this is pi. Negative pi over 2. Negative pi. This one has asymptotes, right? So there's like a vertical asymptote here. These pictures don't have to be perfect. We're just trying to establish something here. Remember that the graph approaches the asymptote, doesn't quite touch it. Like that. Like that. Right, keeps going. Like you have lots of copies of it. The period is only 1, so you have the period is only 1 pi, so you have like a copy and paste over and over like that. This is a graph of f of x equals tangent x. So we want to this is not 1-to-1. It fails the horizontal line test, because if I draw a horizontal line, it's going to touch the graph over and over and over again. But tangent is 1-to-1 if we restrict the domain So I'd like you to think, what do you think is the largest, or what do you think is the most appropriate interval that we could do here? How about if we just get rid of this copy and get rid of this copy? What if we just had this middle area, right? So cut it off after the asymptote and cut it off before the asymptote and just have the middle piece. If you do that, the domain would be parentheses, curved parentheses, negative pi over 2 to positive pi over 2. Curved parentheses. We are not including the actual asymptote itself. We're approaching it, but it's not actually included. So that seems to be an appropriate domain. And then what we're saying is we're just taking this middle part of the graph, and we're going to take that to be kind of the representative portion of tangent. And if we focus in just on that, then we can make an inverse version. So definition. The inverse tangent function denoted tan, little negative 1 up there, is the function with domain. You know how for each of these we've been specifying the domain and range? What do you think the domain is for this one? It's not negative 1 to 1. It's actually negative infinity to infinity. And the range is what we said above. So when you go from a function to its inverse, let me just say something before I finish the sentence here. When you go from a function to its inverse, the domain and range swap places with each other. The x's and y's swap places with each other, so the domain and range swap places with each other. So when we restrict the domain of tangent to be this, that becomes the range of inverse tangent. And the domain of inverse tangent is what was formerly the range of tangent. Seems it's a little tricky to keep track of like the way things swap around, but here, defined by inverse tangent of x equals y whenever tangent of y equals x. I'm using the word whenever. I've used that 3 times today. When I say whenever, I mean that the left-hand side is true whenever the right-hand side is true, and the right-hand side is true whenever the left-hand side is true. This is a two-way street. If one of these is true, so is the other. Sometimes instead of the word whenever, sometimes I've seen people put a double-sided arrow pointing between these two things to kind of indicate that it's a two-way street. So I'll do my little sentence underneath, kind of like I did with the other ones. Inverse tangent of x is the number in the interval negative pi over 2, pi over 2, whose tangent is x. All right. I'll show you some examples. Example, I'll do these, just 2 of them. We're going to evaluate. I mean, when I say I'm going to do a problem, you're always welcome to pause it and try it if you'd like. But I have some other ones in mind for you after these. All right, so I'm going to do these 2. Inverse tangent of 1, inverse tangent of square root of 3. So let's maybe section this off and... All right, let's think about this. Inverse tangent of 1 equals something. I'm just going to indicate it with a question mark for right now. This means tangent of what equals 1. Like, that's what we're trying to find. Tangent of what equals 1. This happens when tangent, this is going to be kind of scratch work. What letter should I use here? We're using x's and y's in a certain way. I think maybe I'll use t. Tangent of t is sine of t over cosine of t, right? It happens when this equals 1. All right, so tangent of something equals sine of something over cosine of the same thing. What have we seen? Have we seen a common value that shows up for both sine and cosine? Yeah, I think we've seen square root of 2 over 2 shows up for both of them. In fact, I know a place on the unit circle that when I take sine of it, I get the square root of 2 over 2. And when I take cosine of it, I get the square root of 2 over 2. So that's a convenient place for us to look at on the unit circle, because then the numerator and denominator will be equal. When you put one on top of the other, they'll cancel out to just give us 1. We're talking about this place on the unit circle. The point Square root of 2 over 2. Now, there's nothing in this problem that told us to look at that part of the unit circle. But I'm looking at this part of the unit circle because I know that the x-coordinate and y-coordinate will be the same. They'll cancel each other out and just give me 1. So the answer is pi over 4. Pi over 4 is the t-value, right? Pi over 4 is how far around we go to get to that terminal point. Again, these problems only have one answer, so pi over 4 is the only answer. And notice that it is in the correct interval. It is between negative pi over 2 and positive pi over 2, which is almost the exact same domain as the inverse sine problems. If you wanted to highlight the part of the unit circle like we did before, it would be this half of the unit circle again. But be careful, because this one, because it has curved parentheses, you're not technically including the endpoints. Almost exactly the same domain as inverse sine problems. We're almost the same. We've restricted the domain of tangent almost the same way we restrict the domain of sine. All right, next one. We want tangent. I'm using t. Maybe I could just use like a question mark or something. But we're using tangent to be sine over cosine. Something over something. And I want the result to be this. That's how I'm thinking about this. You know, there's going to be something up here. There's going to be something down here. In part A, I wanted the two things, the numerator and the denominator, to be equal so that they would cancel each other out and give me 1. But in this problem, I don't want them to be equal. I want them to be familiar numbers that we've seen before that are going to simplify in a way that when I put one of them on top and one of them on the bottom, it simplifies to just the square root of 3. Now, the place where the square root of 3 has shown up the most often is in the number square root of 3 over 2. What would have to go on the bottom? What would have to go in the bottom box, the denominator? What common number that we've seen before would have to go down there in order to make this whole thing simplify to just the square root of 3? The answer is 1/2. These two things do simplify to just square root of 3. So then I ask myself, where on the unit circle does sine of t equal that number, while at the same time cosine of t equals that number? And it happens about here, when we have the terminal point 1/2 comma root 3 over 2. But we want to know what t value is this? Like, how far around the unit circle have we gone? That is one of the common ones that we know. And I'm going to say that inverse tangent square root of 3 equals, this is pi over 3. Pi over 3. And I do a quick check and make sure it's in the correct interval, and it is. It's on the correct part of the unit circle. So we've looked at inverse sine, inverse cosine, and inverse tangent. And I have some remarks to make. About inverse trig functions overall. First of all, I want to say something about the notation. You know how we've been writing these with a little -1 up there? Well, we need to be careful because it's not an exponent. You know, we write inverse functions in general usually as f with the little -1 up there. F with, it looks like it's raised to the -1, but we understand that it doesn't really mean raise it to the -1. It means inverse. So I want to say my first remark is that cosecant of x is 1 over sine x, and that can be written as parentheses sine x close parentheses raised to the -1. But this should not be confused with inverse sine of x. All right, I am saying that the inverse sine function that we talked about today is not the same as cosecant. Cosecant is a different thing. Cosecant is the reciprocal of sine. That's not the same thing as the inverse of sine. Okay? And I'm saying this should not be confused with it, but I will admit to you that the notation that we use is confusing. I wish we had a different notation for inverse, but this is what we've got. We used the little -1, so just be careful to not mix them up. Also, same for inverse cosine and inverse tangent. They do not mean reciprocal. They don't mean 1 over cosine and 1 over tangent. So that's my first remark. Next, I want to say inverse sine as a function is an inverse. And something that we know about inverse functions is that the inverse and the original function are supposed to cancel each other out. So what that looks like is inverse sine of sine x is always going to just cancel out to give you just x. The inverse sine and the sine undo each other. They do opposite things. So they basically undo each other and just leave you with whatever number you had on the inside. In this case, it's called x. And vice versa. If you had them flipped around, the same thing happens. Whatever number is on the inside, x, you do these two things to it, they cancel each other out, they just give you x. And I should say this is true for any x in the domain. Also, the same sort of thing happens for inverse cosine and inverse tangent. My next remark is that inverse sine, inverse cosine, and inverse tangent are also known as arc sine, arc cosine, and arc tangent. So I wanted you to know that in case you see that in a book, in case you see that on a calculator. I actually just picked up my calculator to see what does it call it, and my calculator does refer to them as sine with the little -1, cosine with the little -1, and so on. I've seen some calculators, or maybe I've seen this in like computer programming or something, but I've seen this sometimes referred to as like a sine, a cosine, a tan, as like abbreviations for arc sine, arc cosine, arc tangent. So if you ever see those, I probably won't use those, but if you ever see them, that's what they mean. Same three things that we've been talking about. Got one more remark before we move on to something else. You might be thinking, what about the other three? You know, there's secant, there's cosecant, all that. All right, secant, I'll say inverse secant, inverse cosecant, and inverse cotangent. Remember, this does not mean reciprocal. This does not mean reciprocal. It doesn't mean 1 over secant. This means you take secant, you shorten the domain appropriately, you define an inverse function. I'm just going to say these can also be defined with appropriate domains. And I am not going to require you to know those three. We're not going to talk about those three. But I just wanted to acknowledge that they do exist. You know, you could make inverse versions of those three. Follow the same kind of overall strategy that we did, but use those three functions, and you know, it can work. But basically, I'm not going to really cover them in class or require you to know them, because these three really are not very useful. I think in terms of usefulness, sine and cosine are the most common trig functions. Tangent is the next most common, and those three, we sometimes want inverse versions of them. But as for these three, I don't think inverse versions of these come up in math hardly ever. I think that they hardly ever show up. So that's all I have to say about those. They do exist. Let's talk real quick about... Real quick, I want to say something about graphs of inverse trig functions. By now, you know the graphs of the original trig functions. I'm going to say that we've already said what the domains and ranges are. And we've found a few points. Just over the course of this lesson, as we did a few example problems, every time we did an example problem, I'll just show you, you know, like when we did these, you could say that 1 comma pi over 4 is a point on the graph of inverse tangent. Square root of 3 comma pi over 3 is a point on the graph of inverse tangent. And you could also go back to like the inverse sine and cosine ones that we did. So we know the domains, the ranges, and a few points. So I'm going to go ahead and just draw the 3 pictures and say that I'm, you know, doing this based on what we've covered. Let's put sine and cosine near each other. So this is going to be the graph of inverse sine, which we didn't really draw earlier. You know, earlier we drew sine x and cosine x, and then we sort of restricted the domain, but we didn't really draw a picture of the graph of inverse sine or the graph of inverse cosine. We've said about both of these that the domain is supposed to go from -1 to +1. So when I draw them, you know, that's as far out as x needs to go. For inverse sine x, we said that the range was from -π/2. I think I'm not doing these on the same scale. Let me move that up. Let me move that up just so that my pictures side by side can be the same kind of scale. This will make sense in a minute. I'm just going to move it up to here. Say that's -π/2. And then this is π/2. All right, overall, the picture is going to go from this corner to this corner with a nice smooth curve. And if you were to check and compare it with the points that we've found, everything should check out. Like, I think one of the ones that we did earlier was, let's see. One of the ones we did earlier was the inverse sine of -1, and we found that it equals -π/2. So there's the point, -1, comma, -π/2. So all the problems we did, you know, basically find points for us on these graphs. And for inverse cosine, let's say this is π/2 and this is pi. Inverse cosine of -1 is going to be pi. And inverse cosine of 1 is going to be 0. And we're going to get a curve that looks like this. So similar shape, same domain, but it has a different range. It's up here. What about inverse tangent? You know that tangent kind of looks weird, and you expect that the graph of inverse tangent might also look weird. The next one, you know, the next graph that I draw, I want to say that it is important. It's important for calculus. I'm not telling you the full reason why. It actually takes a while to get there, but the graph of inverse tangent and just inverse tangent in general, not just the graph, but just inverse tangent in general, actually turns out to be kind of interesting and kind of important once you get to calculus 1 and calculus 2. So let's say this is π/2. And let's say this is -π/2. Didn't we say that the range of inverse tangent is this with curved parentheses? So it turns out that it never actually gets to this height, and it never gets to this height because it had curved parentheses. It's actually going to be a horizontal asymptote here and here. And you might say, wait a second, can a graph have more than one horizontal asymptote? Well, yes, it can, as long as it approaches one to the left and approaches the other one to the right. So the graph of inverse tangent goes something like this. All right, so this is y equals inverse tangent of x. Remember we said that this has domain -infinity to infinity? And there's the range. All right. Even though I'm not telling you the full story of like why this is useful for calculus, I will just acknowledge that the thing that kind of makes this one different from the others, and it's kind of special in a way, is the domain. It's the fact that the domain is all real numbers, and that turns out to be a pretty nice property to have for calculus, domain being all real numbers. And it means that you can put in any value you want for inverse going into inverse tangent. And one of the problems that we did was we did inverse tangent of the square root of 3. And by the way, the square root of 3, isn't that approximately, it's approximately 1.7. It's 1.7 something. Put this in parentheses. You know, earlier when we were doing inverse sine and we had inverse sine of 1.25, I said that was undefined because it's off the unit circle. You could never go above 1. Tangent is different. And inverse tangent is different. Right? You know, the graph of tangent is different. It's okay to go beyond 1 to around 1.7, and it's okay to keep going on and on and on forever. You could do inverse tangent of 1 million. I don't know what that would be, but it does exist. I guess you could say inverse tangent of 1 million would be very, very, very close to pi over 2. But it never quite gets there. So to finish things up today, I just have a few problems that I'd like you to try. A few little practice problems. That discussion there where I made some remarks about inverse trig in general, I hope that was helpful. And then the graphs, we did pretty quickly, but I'm glad that we at least discussed them. I'm going to give you 4 problems. I'm going to leave a little bit of space to fill in the answers, but maybe wait till I write all 4 of them. Maybe wait till I write all 4, and then I'll give you a chance to work on them. So A, B, it looks like the 4 problems that I came up with are all for inverse sine and inverse cosine, but we just did some that were inverse tangent, so that's okay. All right, go ahead and take a minute and think about these and pause the video if you'd like, and then I'll talk about them. Okay, so I'm going to put an equal sign next to each of these. And I think I'm going to write a little bit less. Maybe I'll do quick scratch work unit circles or something, but I don't think we need to write so many words and talk about intervals and all that. We did that with some of the earlier ones, but let's just locate where on the unit circle do we need to be and what's the number we're looking for, if it exists at all. You might remind yourself that for the inverse sine problems, we need to be in a certain part of the unit circle, and for the inverse cosine problems, we need to be in a certain part of the unit circle. All right, I think that to get sine, when I see sine, I think y-coordinates. Sine is like the y-coordinates of terminal points, and I want the y-coordinate of a terminal point to be the square root of 3 over 2, and we know a value that does that. It's going to be this part of the unit circle right here. It's going to be pi over 3. We did one that was like that earlier, right? I don't think we did exactly this one. Maybe, yeah, we did like the negative version of this. How about 0? You could ask yourself, do I know a number that when I take sine of it, the result is 0? And it's going to be right here. It's this number right here, which is 0. Sine of 0 is 0. So inverse sine of 0 is 0. -1, I'm thinking, where on the unit circle does the x-coordinate of a terminal point equal -1? Because I see cosine and I think of x-coordinates. Is there a terminal point that has an x-coordinate of -1? There is. It's this right here. Now, there's two ways that I could get to this point, from our usual starting position. I could go counterclockwise, a distance of pi, or I could go clockwise, and it would be -pi. But remember, we are supposed to be in the correct interval. The answer to this is going to be pi. And I'll just say that this is, where am I going to put this? I'm just going to say that this is in the correct interval, which is 0 to pi. Just in case you're wondering, why is the answer pi? Why isn't the answer -pi? -pi is not in that interval. And the last one, there are two places on the unit circle that do this. There's this place here, and there's this place here. But we need the one that's in the correct part of the unit circle, right? So remember, get the highlighter out. We need this. We need to be in the top half of the unit circle for inverse cosine. So you can just rule out the other possibility. And then you just have to ask yourself, all right, what number am I looking for? What's the t value? How far around would I have to go to get here? And it's going to be 3 pi over 4. Because it's 3/4 of the way to pi. All right, so we're going to wrap things up in a minute. I'll just give you a chance in case you're still writing any of this. All right, so that was our lesson on inverse trig functions. And there's one thing I want to address before we finish up. I want to say, some of you might have seen some trigonometry before in another class. And when we started talking about trig, I mentioned that there are a couple of different ways to study it. You could study it in terms of circles. You could study it in terms of triangles. You can also study it in terms of graphs, which we've started doing. We are doing the kind of circle version of trig first. And then pretty soon we're going to start talking about the triangle version. The reason I'm mentioning this is because just like trig functions can be thought of from both perspectives, inverse trig functions can also be thought of from both perspectives. So if you've seen it before and you're thinking, like, where are the triangles? Like, aren't we supposed to be talking about triangles? Just trust me that that's coming soon. And the two different perspectives are going to turn out to be compatible with each other. The inverse trig functions we looked at today are the same inverse trig functions that we're going to look at later with triangles. All right, so just in case there was any confusion there. Okay, so that's it for today. Everybody have a good one, and I'll see you next time.